Hi guys, good afternoon. In this video I'll talk to you about very quick review on where we stopped. So yeah, I asked you to kindly just complete the data cleaning and data treatment over here after we split the data with the percentage at 20/80. My videos for today are based on a different split. My split is 30% for testing and 70% for learning. So your shapes, your data shapes for the X train, Y train might be different. The size of your X train and Y train might be different than what I'm going to be producing with my linear regression in this video. So this is just a disclaimer before we begin. So the last thing that we've done is splitting the data, and also we took a look at the assumptions, the linearity assumption between the dependent variables, the numerical dependent variables, and the dependent variable, so that we can start with our investigation. We also done the multi-collinearity test before scaling the variable. So I suggest that you do the multi-collinearity test before the log transformation of your independent variable. So we start our investigation as usual with importing the necessary libraries. There are sometimes at the very beginning of our course there are more libraries than what we needed, but now we are going to use these. Actually for this semester I was gonna give you two ways of showing how to get the linear regression model. There are two libraries here: the sklearn model selection library, the sklearn linear model, and there's also the StatModels. And surprisingly they kind of give different results, and I wanted to tell you what's the difference between them and all that, but unfortunately we don't have time in this semester, so I'm not going to be using, unfortunately, this second section. We're not going to be using in today's video to create the linear regression model with the sklearn. Okay, we're going to use the stat. So here we're reading the data sets, and make sure that you're reading the data sets after you treated the basement. Remember that the exported Excel sheets from the previous step were having problems with the basement. We have the integer not found. We have the integer not found. We have the integer not found, sorry, and then we needed to fix that with a 0. Okay, so now that we read the learning and testing data after total cleaning and smoothing, here we were able to make sure that the X test and the X train, for example, are data frames and they are the right shape. Then we did the very quick plot for the linearity. Just I'm trying to put in summary everything that you hear: a scatter plot for linearity check between the dependent variable price and all other numerical independent variables. Okay, very nice. So here we have the first assumption it checked. Over here I have certain reservation over why we have all zeros over here, and whether this is really linear relationship or not. This is obviously linear. This is a little bit, could be like light linear. Okay, not as linear. Over here there is a problem with the heteroskedasticity, as you can see. Could be a sign of heteroskedasticity. It's like a megaphone kind of shape, and then you have this stick over here. So there are some certain techniques to deal with this basement. You can split the data set into two logistic regression, linear regression model when the basement is 0, and another when the basement is not equal to 0. And this is one of the things I might ask you to do for the last assignment or the quiz. I might actually lead you through the first step, which is splitting the data into two. One investigation when the basement is equal to 0 and get a linear regression model, and one when the basement is not equal to 0 and get another linear regression model, and see how this step might affect the results. The second step is testing multicollinearity, and please do that before you scale the data with the log transformation. Okay, and then over here we're going to use the StatModel library. With the StatModel library, you can create a linear regression model and fit it using this code. And I like this. I like to start with my students with the StatModel library because it shows me all the output that allows me to explain the linear regression in a better way. For example, over here, I want to emphasize on the idea that with simple linear regression, when you have the dependent variable being investigated with one and only one independent variable, this is why it is called simple, we look at the R-squared. But in our investigation, which is the investigation in real life, we usually look at the dependent variable and multiple other independent variables, so more than one independent variables. In this case, we look at the adjusted R-squared. Looking at the adjusted R-squared over here, we find out that it has a very good reading. Anything over 0.6, sometimes 0.7, depending on your area of study, is really considered good. But when the reading is really too good to be true, as you can see here, 0.999, oh my goodness, I have every reason to doubt it. So too good to be true is also not really good. So if this reading was 0.85 or 0.432 or whatever, I would have been thrilled, more thrilled than now. This is too good to be true. My heart has certain concerns. Shimpai garu. So over here we have the coefficients. This is the AIC and the PIC usually for the all-over fit of the model. And the F statistics, as you can see here, it is below 0.05. So there is a linearity. It says that there is a linearity relationship. And over here we have the different coefficients. What does that mean? The coefficients is the average weight of each variable on related to the dependent variable. So if we take the model, the model will be price equal to the intercept. Actually, I needed to get out the intercept, so you need to get excuse me, the intercept model.intercept, and get the intercept value minus 0.0247 times bedrooms minus 0.1527 times bathrooms plus 0.2284 times floors, and so on, and that will be the model plus the intercept. And here we will not be able to accept these coefficients if their p-value is greater than 0.05. So if this value is less than 0.05, it's okay, we can accept the coefficients. As taking a quick run over here, we find out that this variable, square foot lot, has in fact a higher value of 0.05. So ideally we need to drop this variable. So this is what we're going to do over here. We're going to take the X train and drop the square foot lot from the data. Okay, whatever. Let's move on. So we dropped the square foot lot, and over here I'm gonna drop it also from the training data set so that we don't forget about it. And let's hope that Okay, and then we are going to build the model again. I'm going to build a model with y train, x train, and fit it. Why do I have a problem? I think something happened when I dropped the variable. I think here the code that I used is probably a little bit let me just review the code when we dropped variables. Did we drop here the variables? I think we kind of dropped here. Well, this is what I've done. Learning.drop. Ah, so maybe exit train.drop. I don't need to. Okay, so maybe just like that. I don't need to save it in there. So x train.drop, and this is axes. Axes is one probably rather than columns. Oh no, this is what caused the problem. Okay, let me just take a look at the code again. Sorry guys, I just didn't pay attention when I did the code at the very beginning. And so please be careful with these little things. Okay, and over here we are dropping. So I'm going to take xtrain.shape right now. So here I have a problem. Maybe here I need this. So xtrain.shape. Ah, perfect. So now it's solved. Oh, it's solved. Perfect. So little things does matter. So over here I just mistaken columns with one. So please be careful when you're doing when you write the code. So here after dropping the insignificant variable, I still had the same good reading, the r squared, and I'm gonna again check the p-values. As you can see, all the p-values are below 0.05, so they are all acceptable. Now what we need to do is to generate predictions. As you can see here, we are generating these predictions based on the exit train. So x train, and we're going to get the error on the x train. So the error in the x train, we get it from the actual value of the price minus the predicted value. Or you can use this code, basically model.residuals, resid. And as you can see here, sometimes some of my students may be mistaken y prediction minus y train actual. If you do that, it's no problem because we're going to take the absolute error anyway. So the sign will be switched. So if you want to just make sure that you are having the right order, if the order is important for you, then get the residuals using the model.reset. Now over here, let's check the normality of the error term. So this is the error that we generated. As you can see, the mean is around 0. So this is very important for our investigation, that the mean is around 0 and it is normally distributed. So this kind of assumption is also validated. The last assumption that we need to validate here is the assumption of multicollinearity. It is the assumption of heteroskedasticity. Heteroskedasticity means it is, no, actually the assumption is homoskedasticity, and the check is the check for heteroskedasticity. What does that mean? The ideal scenario is that the variance of the error should be constant, should be the same. Constant or the same is same. Homoskedastic variance. If the variance is not the same, this means that we can't accept the standard error terms. And for those students who took marketing modeling with me, we've done the investigation on Excel on how to make sure that there's an outlier or not based on the standard error. So we take the standard error, and anything away from 3 standard errors, we consider it as an outlier. Or you can check outliers based on the checkbox plot, as we've done earlier. Or you can check outliers based on the z-score. So whatever value is all right, but since we get the standard error from the output with Excel, we use the standard error. And also, because I wanted to explain why we shouldn't be accepting heteroskedasticity, is because of its effect on the acceptance of that standard error, which affects our judgment of whether there are outliers or not, and so on. So in any case, we need to check heteroskedasticity visually and check heteroskedasticity with the Bruch-Pagan test. Visually, we check it by plotting the predicted values, the predicted y, versus the error term. Actually, we need the absolute error. But if you are a curious person and you just want to see how the predicted values are behaving with various errors, as you can see here, seems like there is a correlation between the predicted values and the error, meaning as the predicted values, as you can see, increases over time, the error decreases. So the error is not constant. The error decreases and increases based on the position of the predicted value. So here's the predicted values. The error is very high. As the predicted values increases, moving to the right of the x-axis, as the predicted values increases, moving to the right of the x-axis, seems like the error values here decreases. But in fact, this is not an absolute error, so I cannot really use this for this is just the direction of the error. This is just the direction of the error. So as you can see here, this is 1 to 0.5 minus 0.5, 1 minus 1. It's just the just the location of the error. So usually we take the absolute error. So taking the absolute error, this is the test for heteroskedasticity to check the homoskedasticity assumption. As you can see here, you can probably detect a little bit of a megaphone from right to left. There isn't much variance up to 1, but after a higher than 1 kind of error, we can see here a lot of variance and noise. All right, so to make sure that we get the right answer for heteroskedasticity, we use the Bruch-Pagan test for heteroskedasticity, and also using the StatModels. So today we are just using the StatModels, and we're using the Bruch-Pagan, the heteroskedasticity test of Bruch-Pagan. And here is the test. As you can see, you just say the the class that you imported over here, you use it and you feed it the model residuals, yeah, these residuals, and you feed it the model. It just happened that we called our model, but it's actually here the model fit. And here is the output. As you can see, the output consists of 1, 2, 3, 4 readings. These 4 readings corresponds to 2 statistics. This is the statistics, the first statistic metric, and this is it is significant value, the p-value of this statistic reading. And this is another statistical reading, and this is it is p-value. What are these statistical readings? I added them here for you under names. So the first one is the linear model statistic and linear model statistic p-value, and this is the f statistics, and this is the f statistics p-value. So over here, as you can see, I was able with this code to show you that this is the first statistic, and over here it is significant. And this is the f statistic. With Excel, we take a look at the r squared of the Pagan test, right? The Bruch-Pagan test. Basically, we are taking a look whether there's a linear model or not. Is there linearity or not? And actually, we found out that actually to find out if there is heteroskedasticity or not based on the linearity. So what happens here is the null hypothesis is of the Bruch-Pagan test is basically that homoskedasticity is present. Homoskedasticity is the constant variance. Constant variance is a present. So if we accept the null hypothesis and we don't reject it, if we accept it, this means we are in a good position. Usually when you took in your statistics course, you always reject the null hypothesis. Rejecting the null hypothesis means usually it's a good thing, but over here rejecting the null hypothesis is not good for us, because we're rejecting the idea that homoskedasticity assumption is present. And if we reject that, if the values here of the statistics are significant, this means and indicates that we're rejecting the fact homoskedasticity is present, and we're accepting the fact that there is heteroskedasticity, so there is a problem. So in this case, as you can see here, guys, we had to reject the null hypothesis that homoskedasticity is present, and actually has to embrace the fact that this model is heteroskedastic. As you can see, it is too good to be true. The values here are so high, it's also worrying for overfitting as well. So if heteroskedasticity is present, you cannot use this model. So even though this model looks all good, and this is the kind of case studies that teachers like to bring up to classroom, where the model looks so perfect in the outset, but if you don't check for the assumptions of the model, you might end up using a model that is not supposed to be used. How to fix heteroskedasticity? The first way to fix heteroskedasticity is based on the log transformation, for example, or any kind of transformation for your dependent variable. We already done a transformation. If you want to try transformations, then try the square root transformation, for example, and see how it performs. But since we already tried the log transformation, I would like to show you other ways of dealing with heteroskedasticity. The second way is by redefining the dependent variable. For example, taking a ratio. Over here in our context, we don't have a context like the list of customers, our customers, and then we want to assign a value for each customer based on our overall revenue. So basically how much this customer is responsible for the all over revenue. So basically how much revenue this customer generated over the time horizon over the total revenue will mean the value that this customer brought into our business in percentages. So some customers are responsible for 0.005%, others are responsible for 0.002%, and so forth, if these are customers. If we're talking clients, maybe we're talking about 0.1, 0.2, and so on percent of our total revenue. In any case, we can, in this case, assign a certain ratio, and in this context, it's okay if we evaluate or transform the dependent variable in terms of a rate and then rerun the analysis again. However, in our context right now, I don't think we can do that for the price. These are houses that are already been sold. They are not customers. We want to predict the house prices. I just don't feel that this is the right context for this step, for this data set, or this step is not the right way to deal with heteroskedasticity. Now let's use the weighted regression. Weighted regression or locally weighted regression. The use of locally weighted regression is another way. Locally weighted regression means whenever we need to pinpoint and detect the points, a certain band width, where the variance could be in between certain ranges that we could consider as a constant, yeah. And then it try to based on that, for example. Actually, with locally weighted regression, what we do is we give a weight for each point based on its variance away from our anchor point or the kernel. So with this, we will be able to fix heteroskedasticity. So over here, I prepped this file, but I didn't run the code because I don't want you to use any time right now running this code. because I'm not going to ask you about it for the final. However, I am going to upload this file with the code and a video after the final examinations are over, so that nobody gets confused. So this is this is not a part of what I ask you to do for this semester, because I can't just give you a flip class. In fact, over here I gave you a YouTube. So what's the difference between giving you a YouTube video or giving you my own video explaining this method? What I wanted to have is a session, a discussion, having to ask you questions. Do you understand this? No, I don't understand. So I can explain it in a different way until you guys understand the method. So for this purpose, I just here got you some references that you could use, and the code in Python that you could use for it. Once you have these all defined, then the output will be hopefully will be executed successfully. But in any way, I hope that today you were able to widen your horizon, understand that linear regression is more than just the R squared or the adjusted R squared. You need to test the hypotheses, I mean the assumptions of the linear regression, and also there are ways to overcome heteroskedasticity. One of them is locally weighted regression, that I don't usually cover in my marketing modeling class, and I cover in this class. But this semester we covered so much so far. Hopefully in summertime we can have an interactive Zoom session rather than just a flip video, and we can execute and get a locally weighted regression model and see if we can overcome the problem of heteroskedasticity. As for now, this is it for today. Thank you so much for your attention, and best of luck with this final examinations and with the final course. The final examination will be basically, I will talk about it in due course. Just for now, take care of yourself. If you have any questions, email me, and I can easily go into Zoom to have a video call with you after 7 p.m. Thank you so much.